In these notes today, we're going to be covering average atomic mass and how to calculate that number on page 7. And it is just page 7, which isn't that long, and I know looking at these numbers and the math that we might have to do, it might look kind of scary, but the process is really simple, and all of these numbers are given to you, so you don't have to go and find them. So let's get to it. Something. And actually, before we start on the packet itself, this is just a little kind of simulation, but it has a really good visual depiction of how different elements have different isotopes, just naturally in nature. Magnesium, which is this example I pulled up to start with, has 3 different natural isotopes. And when you have a chunk of magnesium, you're going to naturally have a mixture of all 3 isotopes in there. And so if you just react a chunk of magnesium in the lab, it's not going to be pure one isotope or the other. It's going to be a mix. And if we needed to use the mass of that magnesium to do some calculations, we'd have to use the average mass of all of the atoms that might possibly be in my chunk of magnesium. So you'll see down here on my slide, the average atomic mass is written here. 24.305. That's what you'd see on the periodic table. And that's because we've got a mixture of magnesium 24, magnesium 25, and magnesium 26. And if you look at the abundance in this little pie chart up here, most of our magnesium is magnesium 24. So it makes sense that this average is closest to 24, because that's what makes up most of our mixture. So that's the number we're going to be calculating. And if I clicked around, I could show you a couple other atoms. Hydrogen has 2 isotopes. Lithium is 2 isotopes, although one is major majority. Beryllium only has 1 isotope. So clicking around, seeing some of these. Aluminum just has 1. Some of these only have 1 majorly stable isotope and just a very small amount of some of those others. But just kind of some cool information. Okay, now let's get started with this calculation stuff. Back to these slides. So at the top of your page, it starts by telling us a little bit about the average atomic mass and how we're going to be measuring it in AMUs. That's our atomic mass unit. It's just standardized as 1 proton or neutron should weigh 1. Makes it easier than writing out the actual mass of a proton, which is technically, say that 1 AMU, 1 proton or neutron is 1.673 times 10 to the negative 24th grams. And if we had to do calculations with scientific notation and averaging those out, it'd be a headache. So it's a lot easier just to use AMUs. You'll also see those as just U here. That's what these units for mass are. So that's all that the top really says. We're going to jump straight into actually doing this calculation and finding this average. And this average isn't going to be like most of the averages that you take. There's 3 specific steps we take, and it's not add them up and divide. So get that out of your head. Calculating the average mass is going to be different because we can't actually physically count up and add up the mass of every single atom. Even a tiny chunk of material is going to have millions and billions of atoms. So we're going to have to use the percent composition information, like what we saw in that simulation earlier, and the actual mass of a given isotope. And what we're going to do with those 2 pieces of information, first, we're going to turn the percent into a decimal by moving the decimal left 2 times. So we're just dividing by 100 here, getting it out of percent form into its decimal form. Then we're going to take that new percent with its decimal in its new place and multiply by its mass. You're regularly going to see these depicted like you see here in kind of rows and columns. And so in general, that means you're going to be multiplying your rows together and then add up the products of each row, and that'll give you your answer. So if we go through that process with this first one, my first step is to move my decimal. So I'm going to put that here, move twice on each of my percents. And then I'm going to multiply this first percent by the mass that it goes with. And that equals 43.5353144 keep as many numbers as you can for right now. We will round it at the end. You got a lot of sig figs here to start with that. And technically these percents are exact numbers, so you shouldn't round to 4 sig figs there. I'll talk about rounding when we get to the end. But this second row, when I multiply that new percent by its mass, we get 20.01723858. I moved my decimal, multiplied my rows. Now I just need to add up these two products to get my answer, which is 63.552555298. So now, like I said, rounding with these are going to be a little bit weird, and sig figs and stuff it depends on how carefully you measure these masses. So really, in general, once you do your math and you come up with your answer, we're just going to tell you to leave about 2 decimal places. Never round these to a whole number, but also probably don't need to write out all of these numbers. So you could probably have kind of stopped writing any of these numbers and left off these last kind of 4 digits if you wanted to, because I'm just going to expect you to have at least 2 digits. So I do want you to make sure that that's rounded appropriately and short, just a reasonable number of sig figs and decimal places. So my correct final answer would be 63.55 AMU. And if I'm trying to make sure that I have that right, if I go back and I look at my original numbers, this element, the isotope with the highest percent, should be what my answer is closest to. Is my answer closest to 63? Sure is. So I'm pretty sure this is correct. So let's do that same thing again. So our first step is to move the decimal left 2 times. And on this first one, that's easy. Second, moving the decimal here. But on the second one, don't be tricked. You have to move it 2 times, which means I'm going to have to add a 0 here. Same in that next number. I have to add a 0 to make sure that that decimal has actually moved 2 times. Just going to clean this up a little bit. Okay, so I've moved my decimal. Now I'm going to multiply my rows together and get those products out for each row. And I want you to try multiplying this, making sure you're getting the same answers that I am. So all that multiplication gave me a whole lot of numbers here. And now my last step is add them up. And after I've done that, then that is going to be my final answer. And that should be 20.18 once we've added that all up and rounded it out. Technically, that came out to 20.179444631. But if I just wanted to keep those first 2 decimal places, then the 9 would round that 7 up. Remember, we're not just going to cut anything off. We are always rounding things off when we kind of shorten them down. And so even though we only want to keep 4 sig figs or 2 decimal places here, then we're going to keep rounding that off. And of course, that would have the units of U or AMU, whichever one you want to use there. Checking my answer, my highest percent abundance was pretty much 20, and my answer is pretty much 20. So, looks good. I feel confident in my answer. I am going to ask you to do this next calculation. Same process we've gone through before, slightly different numbers. Just move your decimals, multiply, and add, and get that final answer. Check your answer. I'm not telling you what it should be, but it should be closest to 24 compared to all of these other numbers. Together, let's go ahead and answer this last question at the bottom. This says the element boron has an average atomic mass of 10.81. However, no single atom of boron has a mass of exactly 10.81. Explain why. Well, I think I just mistakenly added in a key word there. A lot of times we'll talk about the atomic mass just like that. Instead of using the word average atomic mass, it just saves time and space. But because of that, people think that an atom has a mass of that number, but it's not. That atomic mass on the periodic table is an average of all boron atoms, not just the measured mass of a single atom. So this is kind of like how I could say that the average mass of a student in my class is 150 pounds. I wouldn't have to have a single student in my class that weighs 150 pounds for the average to come out to be 150. Simplest example of that is if I had a class of 2 students, one of them that weighs 140 pounds, one of them that weighs 160, no one weighs 150, and yet the average of students in my class is clearly 150 pounds. So it's the same deal with these elements. We use that average atomic mass on the periodic table because it's the best representation of the average atom that we might have in a reaction, even if it doesn't accurately portray the true mass of any specific atom in that sample. It's the best number we can use. Now, I'm going to ask you to do a little bit of practice on your own on page 8 in your packet, but I'm going to walk you through the couple of different types of problems that you're going to see there in order to help you get through them, because they're not meant to be tricky. But I know right after doing all these average atomic mass problems, you might look at those first 2 problems and go, wait, what? Am I supposed to be able to answer this with the stuff from page 7? And no, questions 1 and 2, you're going to have to look back just a little bit farther at pages 5 and 6 for help if you need it. Just back to the original definition of an isotope on page 5, and then some of those hyphen notation examples, finding protons, neutrons, and electrons for these specific atoms with this hyphen notation. And for question number 2, all of those atoms are neutral. That's going to be important for you to be able to find all of those protons, neutrons, and electrons. Now, questions 4 and 5 are just straightforward average atomic mass calculations, just like we were just doing. 4 looks a little bit weird, and people are generally scared of it because you don't see that nice table like you do in 5 and like everything else was set up for on the previous pages. But you can make this into your own table. You just need to make sure to find the percent abundance and the mass for every given isotope that it gives you. So it tells us here that we have silver 107 has a mass of 106.905 AMU and a percent abundance of 52%. And if I write that down like that without all those words there, then I'm ready to start moving my decimal and multiplying this row together. And you can do the same with the next abundance of the next element and its mass, and work this out just like a table problem. Or you can just take the numbers from there and do the math just a little bit more abstract than in table form. But those 2 problems should be very straightforward, even though question number 5 has a whole lot of isotopes there. It's the same process no matter what. Now, questions 3 and 6 are a little bit more tricky. It's kind of like that last question at the bottom of page 7, where it made you think about masses and their abundances instead of just calculate it. And question number 6, actually, we need to make some little changes on, because I'm actually never going to ask you to work out a problem quite like this. Even though it can be done, and I'll show you how to do it at the very end of this video, but I'm not going to actually ask you to do that on a test, a quiz, or ever in this class. That's more of an AP chemistry level problem. So a good challenge for some of you, and if you're curious, stay tuned. I'll help you with it. But a more realistic question would be to make some kind of prediction like in number 3 about which of our different isotopes will have a greater percent abundance. Or if I give you percents, like I tell you, I went and I looked it up and did my calculations. My 2 isotopes have a percent abundance of 99.7% and 0.3%. But oh shucks, look at that. I forgot to write down which isotope was which. Is this N14 or N15 here? Well, that's the type of problem that I'm going to ask you to be able to answer and solve. And you can figure that out just by looking at this average atomic mass for nitrogen. If the average mass is 14.007, that number is so close to nitrogen 14 that nitrogen 14 must be the one that has the higher abundance and the almost 100% abundance. So N14 has 99.7% abundance, and that must mean the other isotope N15 has the super duper tiny abundance because it's barely in and affecting that average mass at all. So that's question number 6 all done for you. That's all I need you to do. But if you'd like to go through and do that calculation, stick with me here. Everyone else, great knowing you. Finish out the rest of page 8. And then keep working on your packet, studying for your element quiz or whatever else you need to work on. So to do this math, first we're going to need a little bit more of a formal equation than what we've been doing with that table. And the equation that I'm putting together here is that our final total average atomic mass for these two isotopes is going to come from the mass of the first isotope multiplied its percent abundance in decimal form, so taking that percent, dividing it by 100, and then of course adding that average portion of our average atomic mass to the other isotope's mass times its percent abundance divided by 100. If I'd had 3 masses, then I could have had 3 terms just like this going after each other. But this is technically the formal equation for how we can calculate this. Now, if I go ahead and plug in the masses, because I know them, into this equation, then we get this green form of that same equation. I've just plugged the masses in from the problem. Our average atomic mass was 14.007, and we have the 2 masses of those 2 different isotopes. Now, I didn't fill in the percents because that's what we're solving for, but we'd have a problem if we were trying to solve for 2 different variables in one equation. So what we have to do and kind of understand, and it's something that I've mentioned briefly before, is that our percents are going to add up to 100. So 100 minus percent number 1 is going to be the percent abundance for our second element. Basically, all of the percents of the parts are going to add up to 100%. So if I replace that percent 1 with x, so put x up on top here and 100 minus x up on top there, then I get this blue equation. And now what I'm going to do to simplify this expression is get rid of that denominator. That divided by 100 on the right-hand side of my equation is in both of my terms, and I don't want that there. It makes everything a lot more complicated. So I'm going to multiply everything by 100, and that gets us this purple version of the equation, and all that's really happened is that my hundreds have disappeared over here, and I've moved my decimal twice here because this side of the equation has also been multiplied by 100. And now we're going to attribute this 15 times 100 and times negative x, and that gets us this version of the equation. And now we're going to combine like terms. So I'm going to be subtracting that 1500.0108 to get the non-x terms off of this side. So that's going to cancel out and put that number over here along with the 1400.7 that doesn't have x. And then I'm going to take this 14x minus this 15 and something x and combine those terms together. That gets me a much simpler equation. Negative 99.3108 equals negative 0.996368 times x. And then, of course, all that we need to do to solve for x is divide by that number that is next to it. And if we do that to this side, then we're doing this to both sides. And that cancels this out to give us x on this side. And if I plug this negative 99 number divided by negative 0.99, then that tells me that my x is equal to 99.6728. And since x was my percent abundance of this first isotope that weighed 14, then that means that my percent abundance of nitrogen 14 is essentially 99.7, like I showed you on that last slide. And subtracting from 100, that means that my nitrogen 15 has a percent abundance of 0.3%. So math itself isn't that complicated. Really what it takes is knowing how to set up that information and that calculation in its formula form in order to be able to get to this final answer. But yeah, this is not really honors level stuff, but I'm glad you stuck with me if you've made it this far. So now just get working on the rest of your page 8, and it shouldn't take you too long. Have a good rest of your day.